your IPC subnet using two primitives we have, actors and syscalls, built-in actors and custom syscalls. What I'm going to do here is give a very brief recap about IPC subnets and why you would want to do this. Then I'm going to go through a very brief showing of deploying a subnet, and then walk through some of the code around customizing, creating a syscall, and creating a built-in actor. So some of this is going to take some recap of some of the other sessions that have happened. So like I said, I'm going to go through this fairly quickly. If you want some more detail about this initial part, there was a talk that I did as part of the kickoff that goes into more detail on IPC, what it is, why it is. You can get that from that QR code there at the top. And then my colleague Sarah yesterday did a walkthrough of deploying your custom subnet, or deploying a subnet on IPC. And she walked through like the full steps and everything. And again, her video is there. DoraHacks have put these all up and published them straight away, which is great. So you can refer to that, and there's a QR code there that will take you to that. But that being said, I'm going to go through it very briefly as part of this, just to bring everybody up to speed here. But if you want more depth, then you can go there. So a quick recap about IPC. So IPC, Interplanetary Consensus, is attempting to increase the scalability to a planetary level for Web3, right? So at the moment, you have Web2 systems that have very, very high throughputs. Typically with blockchains, they are much lower because you have a consensus mechanism and you have to get consensus on that. The idea behind IPC is to create a subnet, a hierarchical subnet system in which you can have subnets that might be as small as a data center, or might be as wide as a planet, or go between planets even, right? So the idea behind IPC is it's infinitely scalable because it allows you to create these recursive blockchains. So rather than just say like a layer 1 and a layer 2 that you might have on other blockchains, you can have a layer 3, layer 4, layer 5, and you can arrange those in various different ways depending upon the scalability you want to do. One of the great things being is it allows a deep level of customization. And this is what I'm going to demonstrate here on this, because you can tune a network to have whatever custom gas token, gas schedules, membership rules. It might be permissioned, it might be permissionless. And so you can define all of that within your subnet. And it's also modular as well. So we use the Filecoin virtual machine, FEM, which is a polyglot virtual machine, and we have an EVM layer on top of that as well. But you could deploy your own virtual machine on top as well if you wanted to. And again, because you're running your own subnet, you have that customizability. But you can then anchor your subnet into one of the main public blockchains, say Filecoin, and you get then the security of Filecoin. You can actually access the functionality on Filecoin as well, right? So as I kind of showed, IPC, you have a main net. So in this case, say Filecoin, but it could be any EVM subnet. There's even people that are looking at interfacing it in with UTXO networks like Bitcoin. So you could have, say, layer 2 networks that might be for a particular application, say gaming or databases. Particular games might have like a layer 3, and then you might have regions that might have, say, a layer 4, right? So you can create this however you want. And so, yeah, very similar to what I'm saying here. Now, this is getting into the meat of it, is that you have this customizability, right? So thanks to FEM, you get the EVM runtime compatibility on top, so you can deploy Solidity smart contracts. But what we're going to do today is we're actually going to write a custom actor. So what are referred to as smart contracts in most other languages, at the native level are referred to as actors in FEM and on Filecoin. And so we're going to create a built-in actor, a bit like a pre-compile, that is then available from, say, Solidity smart contracts. The reasoning for this is it gives you a lot more flexibility. So as you'll see in this example, we're going to be actually accessing stuff outside of the EVM sandbox and actually on the host itself, right? And we'll talk a bit about what you can do with that, why that might be useful as we go along. So Let's see here. Oh, and another quite interesting thing here is you can have dynamic life cycles for blockchain. So you could create a ephemeral subnet that is just for a particular task, for example. So you might have some sort of compute job that the blockchain doesn't need to last around long term, but for the duration of that job, you want to have a consensus mechanism to ensure that the rules of the network, the rules of the job, however it is, are being followed. And this thing gets into the realms of very similar to kind of elastic compute, right? Because you can spin up a subnet, do what you want, and then tear it down again, for example, right? So this is not something that's necessarily possible right now, but you could simulate it and play around with it at the moment still. So I mentioned previous talks again. I'm just going to bring these slides up here if anybody wants to scan the QR codes. A talk in which I went through what I've just talked about in a lot more detail. And then yesterday, my colleague Sarah Tiem did a talk that's going through deploying your own subnet in a lot more detail. So what are we going to do today? We're going to go through this pluggable syscall tutorial. There's a QR code there that will take you to the documentation. So docs.ipc.space. We've just published a pluggable syscall tutorial there under the development guides. We're doing a lot of work on the docs at the moment because a lot of this development is going on very rapidly. So things will move around, things will change a bit. So this may change location slightly within the documentation, but hopefully you should still be able to find it kind of going forwards into the future. But anyway, here's where we're going. So what do we need to do here? So we have this pluggable syscall tutorial. First of all, we need a subnet. And there's a quick start here on deploying your own subnet that talks you through the process. Now, I'm going to very quickly run through this just to show where I've got to. The main difference I've done here is I'm using a branch of the IPC Git repository called custom-kernel that has this example in it, right? So although it's called pluggable syscalls, at the moment, it's not actually that pluggable. You have to actually put the code into the repository. So you have to fork the IPC repository and put your code in there. I'm going to walk through where you do that. But like I said, first of all, you need a subnet, right? So I'm going to run through this really quickly. Sarah did a much more in-depth detail of this yesterday. First of all, we clone the repository here. Now, as you see, I check out this particular branch called custom kernel that has the changes in that we want here. I was in the wrong directory, so I then go into IPC, try that again. There we go, it's succeeded. I then try to build the contracts. Again, I got the directory wrong there, but there we go, cd IPC, cd contracts in there, and then run this make gen, and that will compile the contracts there, drop down a directory and run cargo build release, right? All of these instructions are in this quick start here as well. So it does a bunch of compiling here. This is why I'm skipping past all this, because this actually takes a little bit of time to do. And keep going, compile. There we go. So we have it compiled, and we have our IPC CLI command, and we have fendermint there as well, which is the actual sort of daemon we're going to be running for the network, right? So let's see here. I look in my config file, and one of the things you'll need to do is ensure that the gateway address and the registry address are correct. If you look on the documentation here, you'll see what the current gateway and registry addresses are. These are tied to our CI/CD system at the moment, so they're deployed automatically. So these will change, but the existing ones will obviously stay around. But you might not have the same functionality as things go along. So just double check that when you do this, when you run this, that you've got the gateway address and the registry address the same as what is in here, because they will change. So I've done that. I've created a new wallet. I have created the subnet here. We're just going for one validator here. So rather than 3 that is mentioned in the documentation, just for brevity. And I go to once I've created the wallet, I then can go to the faucet and send some funds to it. So this is all detailed here. Create a wallet, go to the faucet, send some funds to your address. Then we create a child subnet and join that, right? Again, I'm going through this rather quickly because this was all covered in Sarah's talk yesterday, so you can go back and watch that. So there we go. I started up. It fails at first because I haven't actually got Docker running. I restart Docker and then try it again, and it all then starts to spin up, right? And we end up at the end with a subnet node is ready. So we actually have a node running on the network now, and it has a ETH API, and it has a chain ID. So I can go into, say, MetaMask, and in here I can set a custom network up. In here, if I go into settings, you'll see networks. I have here IPC local subnet, and you can see I've put in connecting to localhost on 8545, and I've got the chain ID there as well, right? So that's all set up there. I used the faucet to send it some funds, so it does have some funds here. It had some funds sent to that. But I've created, this is actually connecting to my local subnet, right? And I created it, when I set it up, we just created it to have one token in it, one TFIL. All right, and I've done some contract deployments to it yesterday, so that's sort of dropped down a little bit. But I'm able to directly deploy contracts to my local subnet. So how do we do the customization, right? So we've got a subnet going. Here we've got this pluggable syscall tutorial. Now, again, I'm not going to go over, I'm going to go through this, but I urge you to go through and read the tutorial here to find out what's going on. Now, first, a little bit of background. We have two things here. We've got custom syscalls and we've got default actors, right? Custom syscalls can access outside of the sandbox. So in this case, they're going to actually access the file system of the host itself. So imagine you want to do something where you want to access some other device or something that's outside this network. Now, one example used here is, say you want some randomness, and maybe you have some hardware random device or something that you want to access. Well, you could create a custom syscall to do that. Once you've created that syscall, in order to really kind of exercise it and use it, you're then going to need an actor. A built-in actor to access that. That has to be written in Rust. You can't access a syscall directly, a custom syscall directly from Solidity at the moment. Hopefully, we're gonna provide a way to do that in the future. But at the moment, you'll need to create a built-in actor in Rust to access a syscall, and I'm going to talk you through that as we go through here as well, right? So you don't need a syscall for an actor, so you can just create an actor. An actor on itself can't access kind of outside of the host, but it can't access data outside the host, but it could refer to libraries that are not native, for example. So one example might be something that you can't do in Solidity, at least not very easily, is do something like parse JSON. Well, you could create a built-in actor that is a JSON parser, for example. That would be a really interesting project. If anybody wants to do that as part of the hackathon, that'd be a great example, right? So creating a JSON parser and create a built-in actor that uses that written in Rust that you could then call from Solidity and give it, you know, a chunk of JSON, and it could pull out a particular attribute from that JSON, for example. That'd be a fun thing to do. So we're going to, first of all, I'm going to walk you through the code here. So let's see here. So we want to define the syscall to start with. So all of this is in Rust. And as I mentioned, so there's links in the documentation to all of the code and the lines in here. We're in a branch called custom-kernel that's in here. Custom kernel, that's the branch. This is a permalink, so it's linked directly to that that commit there. But anyway, so first of all, we define our syscall here, right? And what we're going to need to do is create a custom kernel that syscall fits within. So we define that. We need to define a struct here called custom kernel implementation, which extends the default kernel. We're going to use a crate called ambassador that automatically does this call delegation, and that reduces boilerplate code. We don't have to then manually go in and do those delegations ourselves. We can use that, and I'll delegate them to the underlying implementation of the default kernel for the majority of these things here, right? So we need to implement then the necessary functions for our syscall. So here's the actual meat of what we're doing here. Here's our actual syscall. So we've got this function, my custom syscall, and what it is actually going to do is read the number of files, number of paths in the root directory of the node it's running on, so on my machine. Now, I'm running this on macOS. You can do all of this on either macOS or Linux. We have instructions for setting up the dependencies for both there, so it should work either way on that. So we get a list of all of the files, and we're going to return a count of those files as a unsigned 64-bit integer there, uint64, right? So this is the guts. This is our actual custom functionality, right? Now, just to recap, we're doing this as a custom syscall. This is a bit of a trivial example, but what it is showing is accessing outside of the EVM, outside of the virtual machine, because what you were doing, you're getting outside the sandbox here. So there be dragons. So now we're going to need to implement a kernel trait for our new custom kernel implementation. And so we have the code here for this. And this, sets things like, the amount of gas and, how gas is charged and that kind of thing. That's reasonably boilerplate. You can copy that over as you need. The main thing that if you do this, if you go through all of this code, this is really the main bit you're going to need to change, just this bit here. The rest of it, I'm just going through to explain how this all kind of links together here. We need to link in the syscall here. And so this is here in my custom kernel.rs. Here there's an examples directory here within IPC, and that has some examples here, including this one that we're just going through now. So we link that. We've got the implementation. We've got the syscall. The syscall can then be exposed publicly, and we can then call the syscall in this fashion here, right? So we can then call the syscall here. Now we've created that in a custom kernel implementation. What we now need to do is we now need to tell IPC to use our custom kernel rather than the default kernel that's in there. And in exec.rs is how we do that. And we set the executor here to be our custom kernel implementation, right? Again, for the purposes of this hackathon, you should be able to copy all of this fairly straight through and use it. So we've done that. Now, in order to access this syscall, we're going to need an actor. So we're going to create a what's called a built-in actor in Rust. So this is the second level of customization. You can do an actor, but it's really the only way to kind of exercise and test and show a syscall kind of on its own there. So here is this actors.rs here, and in here we register our custom syscall, and we can actually then invoke that as well with the actor. So when invoke is called on this actor, we actually call that syscall and return the value from it there, right? So yes, what we note here is whilst it is Rust code, IPC is actually going to compile it to WASM, because if you remember, as I said, it's a polyglot VM. It actually runs WASM. right? So the Rust is actually compiled down to WASM here. We need this shared.rs in order to set things like the custom syscalls actual name there as well. And we need this lib.rs in order to actually export the actor so that we can then access it, right? So we've kind of gone through all of these steps here. And then the main thing we need to actually do is load the actor at Genesis, to deploy it at Genesis. So when we create a new network, we need to actually create this. So within FVM, there's genesis.rs, and within there, we put in a clause here to actually create our actor, right? That means our actor is now available for use from FVM. Now, we want to test our actor. Now, we've got our actor. It's written there in Rust. Now, there's two ways we can go about that. One is we can create some code that executes it as part of the process of the blockchain kind of advancing. That's what we're going to do here. You could also do something like within Solidity access it. So here is some Solidity code I've created in which we test a custom actor here. The actor's ID is 49. That was something that was set in our code here. When we actually created this, we set the ID, I think it's further up here somewhere. We set the ID of this to be 49. Can't see where that is, but that's in here somewhere. We set the ID to be 49 for that actor. And then we're actually calling the actor by ID. And we actually have this actor library as part of Filecoin Solidity that makes this a little bit easier. So actor call by ID, we pass the actor ID in. There's some parameters here about how we should marshal arguments in to this actor. In this case, we don't send any arguments, so it's none codec. We're sending a blank byte here. We don't need to send in any arguments here. And this is whether, how much it needs to be paid in order to execute, and whether or not it is, I believe that's whether it's idempotent or not. So you can set that to whether or not it executes that. We then need to jump through a little bit of a hoop to take our bytes back and reassemble and turn them back into an integer, but we can then do that and return the number. So we can actually execute this within Solidity, right? However, the other way of doing it is to actually execute it and invoke it from the Rust code itself here. So that's what we're doing here. We're going to go through, we can actually set here within exec.rs that what we want to happen is we want this code to run every new block, right? So every new block height, this will run here. And the key thing here is at the end here, this print line that we have here, custom syscall actor returned, and we've got the value that has been returned from the actor. So how do we test it? We can go ahead and build this here, and that will bring that up to date. Now, I actually, because we checked out this example branch and then we built it, we've already done this step effectively through this build step here. So we've already got it here. So we now have it actually running, and I have a Docker image running. And if we look here, and if I get the logs from that Docker image and run that, we'll see, and this is actually executing. You can actually see this is currently running. So every block, which is about every second or so, we're getting this custom syscall actor returned 21. So there's 21 files in my root file system. Yeah. Okay. So that is showing, just to recap here, we created, first of all, we created our own custom subnet, and we connected that to, in this case, the calibration testnet on Filecoin. That was all covered in Sarah's talk yesterday and in the deploy a subnet quick start. We then, but we checked out a branch called custom -kernel, and that custom kernel, we've got all of the boilerplate in there that's explained in here as to how you create your custom syscall, register your custom syscall, create a built-in actor to call your custom syscall, and deploy that actor so that it can be then called. And then right at the end here, we actually ask the blockchain to execute that every block. So every block height gets executed, and we get this debugging output here just to see it actually executing, right? So hopefully that's a bit of a whistle-stop tour there. Like I said, this is all documented in IPC docs. We'll be adding some more documents in here. There will also be soon some more conceptual documents on pluggable syscalls and on custom actors. But there's documentation here, and there's some links to some background information here as well for this pluggable syscall tutorial. Like I said, a lot of this is moving around. So if you have any trouble, then please do ask on either Telegram or in the Slack as well. Great. So yeah, we have a Telegram group here. So join that as well. Opening ceremony, that's happened. Workshops were in. Submission deadlines at the 31st of March. Winners will be announced the 7th of April. We're really looking forward to see what you're building. This allows you to really push blockchains in a much more customizable way. Yes, it's a little bit complicated. You're going to go through, a few hoops at the moment. There's quite a bit of boilerplate code to go through. We're going to be simplifying that as we, in the future as we go along. But it'd be great to see what you create. How can you interface a actor, a smart contract within a custom subnet to some other functionality that you might not be able to access from a blockchain? Like I said, it might be a randomness source or some sort of parser or library or something like that that you don't have default access to. Okay, fantastic. So thank you very much, and I'll hand on back then.
Thanks a lot. Thanks a lot, Matt. Yeah, for everyone watching, like Matt said, a lot of things are moving in progress. So where you can find help. It could either be the Discord channel, or it could be the Telegram channel dedicated to the data economy hackathon. And yeah, you still have a few days at hand, close to 39 days at hand. So yeah, take your time, go through all the docs available, go through all the resources available on the hackathon page, and everything that is being shared by the Filecoin team and the other sponsors and partners of the hackathon. And yeah, I wish everyone a very good luck in their building journey. Keep building and breaking. Thanks a lot, Matt.
Great, and just one more plug here. We're going to be in ETH Denver. We'll be in Denver for ETH Denver. There's also the Phil Dev Summit, which is the Filecoin Dev Summit that's going on as well over the next week or so. And I'll also be at ETH Global London, ETH Oxford, and the Oxford Blockchain Hackathon. So if you're at any of those locations, either in Denver, Oxford, or London over the next couple of weeks, keep an eye out and come say hi if you need any help. I'll try and help you there.
Yeah, thanks a lot, Matt. Where Matt would be. Find him and pick his brain on all the stuff that you've been wondering about. Thanks a lot. Take care, everyone. Good luck for the hackathon.